My name is Fiona Aldous, my colleague, Elizabeth Cassin. We're going to be co-presenting here this morning on Building Enclosure Commissioning. We're going to touch a little bit on the commissioning process unto itself, but really we're going to focus on the types of tests that you would typically see in your commissioning experience. So we're going to run through just the generic stuff. Both Elizabeth and I work for a company called Janney Elstner, and it began as a forensic company, and it's an interesting start also for commissioning, right? Because we're trying to learn from the mistakes that have been made so that we don't recreate them. And so a lot of savvy clients figured out that these mistakes are being made. Janney Elstner figures out how to fix them. Let's try and prevent them and in the future. And henceforth, we really got from consulting into a more commissioning-based practice. So we still do a lot of both, and I think that's really critical because you're always going to be encountering new conditions, especially with building envelopes. They really seem to push complexity, design, new materials and such, so you're always discovering what kind of problems are happening, and you may not have always had seen them before. So what does constitute the building enclosure or envelope, depending on what side of the body you like to refer to it as? Well, essentially it is all 6 sides of the building. The concept is that we are containing the condition space, the mechanical, the temperature, the relative humidity, per the design conditions that are established by ASHRAE or by the owner or by the mechanical designer. So it's not just what you see above grade. It's not just the pretty facade, it's not just the windows, it's not just the curtain wall or the cladding or such like that. It includes all components of the roof, the penthouses, and it includes every part of below grade. Below grade is critical because we get really only one chance to address below grade problems. And obviously, the deeper we go, the more issues we may encounter potentially with groundwater, the more problems we can have potentially with infiltration and such, both from below and also coming in through the sidewalls. So when we think about envelopes, we really have to think about these complex designs that architects so commonly now like to employ in buildings. And we're thinking about, again, all 6 sides of the building. So not too many buildings have 6 sides these days. They're going to have multiple. And that's really where the challenges come in a lot of today's architectural designs, because they are not simple. Architects are always looking to integrate new materials, new forms. Computer software is driving the design into more complex shapes, more free-form flowing shapes. And so the materials and the performance is always being challenged continuously by architects and their design inspirations. So the building enclosure commissioning process, it really did evolve out of consulting. The consultants have been working on improving or helping architects to develop details for a number of years, and then all of a sudden, hey, it's commissioning. It's a much nicer term. It refers to more of a comprehensive process, but essentially the idea still has its roots in the consulting world. So back in 2006, I was part of a committee of about 20 people or so. We got together, consultants in the industry, and said, okay, the National Institute of Building Sciences was charged by the DOE with the mission of developing a comprehensive suite of commissioning documents. So it went from Guideline 0, which you're all familiar with, to evolving into elevators, fire suppression systems, smoke control, etc. The idea was to have the whole spectrum of documents to facilitate whole building commissioning. Well, the practice never quite got off the ground, but one of the guidelines that really did come to fruition was Guideline 3, which is the building enclosure commissioning process. So that really is the founding document for how we practice enclosure commissioning today. In 2012, there was 4 of us that got back together and figured out that really what we had written in 2006 was exceptionally complicated, not exceptionally relevant. So we rewrote it today to become Guideline 3 2012 version. Currently still available on the Whole Building Design Guide and still for free. It is not, as was referenced yesterday, part of the ASTM family of documents. It is still available. So I highly recommend that you pursue getting that if you're interested in building enclosure commissioning. The biggest value in that document is also the appendices. So there's a lot of checklists, there's methods of approaching commissioning, there's specifications, so it's a really worthwhile document. If the first 40 pages or so put you to sleep, don't worry, you'll find some value back in the appendices to kind of wake you up again. Okay, so in 2012, simultaneously with the rewrite of Guideline 3, developed the ASTM standard practice. Now, there was an agreement between NIBS and between ASTM that Guideline 3 would go away when the ASTM E2947, the standard guide, was adopted. Thankfully, that hasn't happened. You don't have to pay $50 or $60 for an ASTM standard to figure out how to do building enclosure commissioning. So the ASTM standard guide is available, as is the standard practice from ASTM. But essentially, they do parallel Guideline 3. So essentially a working in order. The ASTMs are constantly under revision and are pending and changing as we speak, every meeting type of thing. One of the big things that has evolved in the ASTM standard is the table of testing. It's gone from being phenomenally comprehensive to being by choice and down to very simple 5 or so tests, which is what's currently being balloted. So interesting transition there. There's also a note that identifies that the testing is optional based on the owner. So also what's under development is the Building Envelope Thermal Performance Verification Commissioning Program. It's an ISO document. I happen to be convening that working committee, and so that one is also coming together on a more obviously global level. So what leads us to a lot of commissioning today is LEED, right? And probably that's perhaps why you're sitting here, because LEED version 4 now has a component of building enclosure commissioning as part of fundamental commissioning. So what that does require us to address is the OPR, the basis of design, and one single design review. So it's a very limited inclusion of enclosure commissioning in LEED, but it really is a step in the right direction, because at least if you're going to find value in the process at all, it's going to be in the design review. The stuff that you do up front versus obviously just having to do a bunch of tests at the back end of the project. Enhanced gives us an option for 2 points under the the V4 commissioning, but it does also require a comprehensive process, and the process that it references is Guideline 3, 2012. So that does also include, beyond what's identified in in Guideline 3, some requirements that really seem to have kind of been adopted from mechanical commissioning land, which includes current facility requirements plan, operations and maintenance plan, training, and an ongoing commissioning plan. And these are all requirements that when we do submit to LEED, they do need to see that checkbox. We've kind of been going through that process. So it's a bit weird, but we try and adapt, as enclosure commissioning has been adapting all the time to kind of its MEP predecessors, where like the slow stepchild coming on board, using similar terminology, but all kind of happening a little bit at different kind of time frames. So where does testing actually fit into the commissioning process? So the commissioning process that's outlined here is really kind of a bullet point, if you will, of Guideline 3. It involves the kickoff commissioning meetings, development of the OPR, or assisting with that, review of the basis of design, design reviews, building enclosure commissioning specs and plans, and then possibly evolution into a mock-up, if the project requires it, some testing, submittal reviews, possibly shop visits, pre-installation meetings, construction observation. All of this is happening before actually you get to the point where you're going to be doing field testing. So field testing really occurs not at the end of the project, as you may be familiar with MEP, but really as we begin to install components in the field. So it's pretty critical that obviously that testing does occur at that time. Otherwise, we really have kind of missed the boat. It's one of the challenges with doing whole building air testing, is that we really have to wait until the end of the project in order to do those tests. So what happens at that point in time when we do have a problem? Fitting into the whole context of the commissioning process, we have the issues log, final commissioning report, warranty, and the continuing facility requirements. Why do we test? Okay, we test essentially to reduce our risk, because really commissioning is about how we're controlling risk, identifying the risks, figuring out how to mitigate them, figuring out that the installation, what the performance requirements are, and then subsequently verifying that we've actually, or the installer has actually met those performance requirements. We want to avoid unintended consequences. There's nothing like having a laboratory, a data center, or art museum, or such like that, that has a water or an air infiltration problem. So testing, design reviews, the whole commissioning process is really about how to avoid those kind of long-term related problems. We verify the performance also meets, as stated by the owner. You know, what are their expectations? Are we meeting the goals that they've set forth in the owner's project requirements? How much testing is enough? You know, who determines that? Keeping it real, that's really where it comes down to, is let's not test for the sake of testing. So one of my projects here, we had a performance mock-up, and the guys actually, the contractor itself, forgot to purchase this test, right? And it was a point load test for these sun shields. So what did we do? The installer, who happened to be about a 300-pound Canadian, decided all of a sudden he would jump up onto the screen here and determined that, yeah, it actually did meet the point load test, physically himself hanging off the top of it. So it's a nice example of keep tests real. You don't have to necessarily have all the gadgets, have all the calibrated equipment. There's a lot of different ways in which you can verify performance without having to be a certified testing agent. One thing I realized that I did neglect to talk about earlier was that there was a question earlier that came to us prior to the presentation about certifications of building enclosure commissioning providers. And currently the only one that I'm aware of is by the University of Wisconsin. And so that's a 3-day class. The one that was being proposed by ASTM has been abandoned. It was a NIBS ASTM collaborative effort where it was going to comply with the ANSI requirements of an educating body being separate from the certifying body. But middle of last year, ASTM decided that that was an effort that was going to be just a little too expensive and a little too time consuming. And so that certification effort has actually gone by the wayside. RCI is starting to pick up something, so they may pursue that concept as well, but right now it's only the University of Wisconsin. So what kind of tests are performed and how are they performed? And who determines what tests are performed? Well, basically it is the architect. They have obviously that basic set of specifications that has the default test as part of part 3 hidden back in the end of the specification. They have to make sure that that test is relevant to the actual building systems that they're working on. ASTM is going to tell you how to do your test. It's not going to tell you where to do your test necessarily. It's not going to tell you what the pass-fail criteria is. Though that is all information that you as the commissioning provider or as the architect need to include either in the specification or in your building enclosure commissioning spec. It's important that the type of tests are fully defined within the spec, so the contractor is familiar with what they have to do and when. It's also important that what the criteria or the allowance for pass-fail is identified, because sometimes these tests will not exactly comply with the owner's project requirements. Are the tests appropriate for what the systems are? For example, roof testing, right? Do we want to do a flood test on a single ply membrane with insulation and a concrete deck? What if we do find a leak? How quickly do you think that water is actually going to migrate from the membrane through the insulation that acts a bit like a sponge, through the concrete deck, all the way to the interior? So is a flood test appropriate for a single ply or a built-up roof membrane system? So these are questions that you need to have an understanding of what the actual system and the assembly is before you go specifying the tests. Then subsequently you really need to understand the nuances of the test. Are they appropriate? Are they going to actually give you an understanding of whether you've met the performance intent or not? So who performs these tests? Do you need to be certified to perform these tests? Okay. According to ARMA, our nozzle test, everyone's familiar with that, right? Everyone's kind of watered a garden before. Okay, the nozzle test, ARMA 501.2, it requires you to be certified as a ARMA testing agent in order to perform that particular test. Does the building enclosure commissioning provider do the testing? Does the manufacturer or perhaps some other or the contractor? Okay. I really do recommend that it is the contractor that performs these tests. Hold them responsible, put the contracting entity the responsibility fully in their court, such that they do require to coordinate fully access to the test areas and all of the other logistical aspects that goes along with it. I've spent numerous days, unfortunately, with a testing agent under my contract, having them arrive on the job site and say, well, I'm here, okay, you got to pay me for that day regardless of whether I pull my certified calibrated nozzle out or not, and pay me $3,000. Only to find that I can't get the contractor, I can't get my test agent onto the side of the building like I need him to be because they're doing some other kind of safety training or they've had some other kind of problem. They don't have hoses long enough. We don't have the right water pressure to the job site. So all of these are challenges that come along with testing that ideally you want to put the responsibility back onto the contractor to ensure that they really do meet all of the objectives of being able to perform the test. So when is testing performed? Ideally, it's going to be performed as early in the project as possible. Mock-ups are terrific, whether they're a laboratory mock-up, an in-place in the field mock-up, or an actual first installation on the building. They all give us an opportunity to learn something. And that is so critical that we do that exercise before we go and apply those same practices throughout the entire building. So we do test throughout construction. There's going to be peaks and flows, if you will. We're going to want to test early and then we're going to test probably routinely throughout. We're going to need to repeat the same tests over and over. Possibly not. There may be some tests that we get a comfort level with, but then we want to just test specific sampling of the additional areas. Do we test at the end of construction? Well, sometimes we do. Thermal imaging does require us to be a fairly conditioned building, a temperature differential, so it does require things wait until the end of construction, similar to our 1827 or 779 whole building test. The difference really that lies between building enclosure and MEP is that our testing has to be done during construction. Okay? We can't wait until the equipment or everything else is installed at the end. That simply really misses the whole point of the envelope commissioning process. And I realize that the ASHRAE has our 3 paths of meeting our air barrier requirements by code, one of them being the whole building air test at the completion of the project. But I really think that does miss the point, and too many opportunities for problems can be identified along the way that you really are going to miss if you leave it right until the end. It's important that your contractors include testing in their schedule. Otherwise, it's just not going to happen. If they don't include it, they're just going to run right by it. So the point to note is that it's got to be there, otherwise it will just get ignored. We test risky and complicated details. We test when numerous trades come together. That's always kind of where that can possibly happen. I'm going to blame that guy, he's going to blame that guy. The by others type of statements that are too frequently found on drawings. Typical systems to establish baseline performance. So we may be comfortable with our stick-framed standard curtain wall system, but we just want to verify, hey, that we are really achieving that level of performance. We want to get a representative sampling. And what happens when things do fail? Okay? How many more tests do we need to do in order to feel comfortable that we don't have some kind of a systemic problem? So these are the testing considerations, things that we need to factor into, things that are really potentially a little more under the contractor's control, obviously not weather, but things such as, do we have the proper amperage in order to run out the machines? The water supply, how far is it away? What is the available pressure? Do we have access to where we need to go? If we're only doing 4 or 5 story buildings, it's obviously a lot easier versus something that is 5 up to 50 or such. What is the weather? What are the conditions that we're trying to test, and are they appropriate for the testing that we're undertaking? So example here, when we were testing the laboratory up in Wisconsin, the owner was intent. They really wanted to do a very comprehensive schedule of tests, one of which included evaluation of the thermal performance of the curtain wall system, which meant an in situ basic heat transfer test, whereby we were required to both heat and cool this chamber here. So we have our liquid nitrogen, and you can see that's simulating a minus 10 degree temperature, and essentially what we had outside, based on all the snow, was pretty damn close to a minus 10 degree temperature in Madison, Wisconsin in the middle of January. So some tests are really, sometimes you just are doing what the owner wants. That was their requirement, but I must say that honestly it was a little bit ridiculous. We test interrelationships of systems. So where does the curtain wall meet the masonry? Where does it meet the air barrier and such like that? What happens if we damage the systems? How do we deal with over-testing? Okay? Some people these days are challenged by the fact that we've got a curtain wall that we're testing at 15 pounds. However, we simultaneously also engage the air barrier, which should not be tested at 15 pounds. Okay? How do we isolate the two different systems so that we're not over-testing one area in comparison to another? So we always have to remember, how do we isolate or focus on one versus the other? Out-of-sequence work is also critical. I mean, the contractor is going to scream because he didn't plan to put the sealant joint in around the windows until 3 months later. However, you want to do your window testing, which, guess what, requires the perimeter sealant be installed. So there's out-of-sequence work that's going to have to be accommodated for and paid for. And the contractor is going to want to get paid for that extra mobilization. So on to our case studies. The first one that we want to briefly talk about is air and water tests. Wisconsin Institute of Discovery, basically around a 330,000 square foot building, included the below grade as well as 4 stories above grade. Total project cost of around $200 million, construction over a period of about 3 years. It achieved LEED Gold, and we were the commissioning providers engaged directly by the owner on the project. It had a very, very comprehensive testing program, and that was derived from the owner's project requirements because they wanted a laboratory building that was going to really last 100 years. Their design brief, or their OPR, also included virtually zero maintenance. So there were no exposed sealants on the project at all. Everything was concealed from UV, so it was concealed from all of these major methods of deterioration and weathering that are so often our cause of building failures. So the testing that we started to do, and that I'm briefly talking about, is our basic air and water tests on our facade systems. So it is ASTM E783, which designates a field test of the laboratory version, which is ASTM E283. Okay. Essentially the same tests, but there are changes that accommodate for a reduction of allowable, an increase in the allowable air leakage through wall systems during this test to accommodate for field conditions. So in this test, you're essentially constructing a chamber to the inboard side of the test specimen, drawing, in this example, a negative pressure through the test specimen, ensuring that the equipment is calibrated. We worked directly with Architectural Testing, Inc. on this project. They did all of the testing on behalf of us as the commissioning provider. First, one of the early projects, but also one of the first lessons indicating why it would be more ideal to have the contractor actually do the tests versus ourselves holding that contract. So the air testing, the chamber and such like that is also used for the water testing. So the water testing is essentially a spray rack that delivers 5 gallons of water per square foot per minute over the test specimen. The goal is to achieve a good sheeting of water, and you essentially are attempting to suck water through the test specimen by putting the chamber on the interior side under some kind of a negative pressure. This test also has a difference in allowance for what the test pressures are in the laboratory versus the field. So in this example, this allows for typically a 2/3 reduction in test pressures for something that would be the designated design pressure in the specification. You are allowed, because of it being performed in the field, to reduce those test pressures by 2/3. The associated criteria for pass and fail also needs to be examined, as I said earlier, with respect to whether it meets the owner's expectations. So during these tests, you're going to be observing from the interior side for any signs of water leakage. The water leakage is defined as 1/2 ounce of water that does not pass the inboard plane of the window assembly. So you can actually see water, but it's not actually defined as a leak. Okay? Explaining that to an owner is really, really challenging. They're seeing water, they're saying it's leaking, and I'm saying, well, no, actually it's not. per the definition of the standard. So the types of facilities we work on really don't allow or want any kind of water leakage anywhere on the interior of the building. So we need to rewrite that standard, or not rewrite the standard, but we note within the commissioning specification the requirement that no water leakage is allowed, and the definition of water leakage as defined by ASTM or by ARMA is not to be used on this project. Otherwise, you'll have a terrific argument with your subcontractor. ARMA 501.1 is the dynamic version of this static version where you're constructing the chamber to the inboard side. This testing was pioneered by ATI, having the first system whereby similar that you're going to see down the Everglades here, a fan system with a spray rack mounted in front of it. It's controlled by an engine that calibrates the amount of water and the speed, essentially, of the wind that you are projecting against your test specimen. So in this example, the test specimen, you are on the inboard side, the wind-driven rain is obviously on the outside, and you're looking for leaks again. Great advantage of this test method is that you can do multiple areas, probably up to about a 4-story building, because it's limited by the actual reach of the lift, lifting up the fan. But you can do multiple tests in a very shorter period of time. Test area is about 10 foot by 10 foot, so it's really something to consider if you're looking for that type of testing on your facility. Right, so your 501.2 is your generic nozzle test. It's performed with a calibrated nozzle. It facilitates you changing the dimension of the water stream to be anywhere from a maximum of 30 psi down to really a pencil stream for diagnosing where leaks are actually coming from. Very useful tool, but I must say it lacks the ability to simulate really the wind-driven rain, similar to what you'd be replicating with either the 501.1 or the E1105 under the static or dynamic pressures. So it has its use, but it's also got its limitations. I think it's way too over-specified in the master spec and CSI divisions. You'll commonly see it used trying to verify performance of metal rain screen panels and such like that, where it's really completely, it's a useless tool in that context. All right.
So we're going to switch gears a little bit, talk about roofs. So Fiona did a great introduction to what building enclosure commissioning process is and how enclosure testing fits in with that. Talked about testing for air and water leakage testing for walls. So now we're going to look at roofs. So we're going to look at 2 different types of tests here with this case study. One being impedance testing, so capacitance testing, and the other being electronic leak detection. How many in the room have done these or seen these or are familiar with these? Okay, we have a few people. One reason that these tests are really important, obviously, is the roof constitutes a pretty significant part of the enclosure. It's exposed, it's fully exposed. We got to get it right. It's one of the first things that goes on in the enclosure to get the building watertight, airtight, so we can install finishes and mechanical equipment and such. And because of that, we have a lot of trades walking on the roof, we have materials stored on the roof, we have things dropping on the roof, and there can be significant issues with that if we're not careful. So one of the things we like to do is specify within the commissioning specification doing one of these tests or both of these tests to evaluate the roofing system to see, do we have trapped water in there, or do we have holes within the membrane, or seams that aren't welded. identify basically water within the roofing membrane, or within the roofing system, or defects in the roofing membrane. So the first test, ASTM D7954, is the non-destructive electrical impedance scanners, and you can see that equipment there on the photos on the left. Basically, the purpose of this test is to identify concealed or trapped moisture within an assembly. So we can use this test on single ply or built-up roofing, so coal tar, asphalt, mod bit, TPO, PVC, and the membrane needs to be non-conductive. You also need an insulation or a moisture-absorbing material below the roof membrane, because what you're doing is you're creating an electric current through the non-conductive roofing membrane, and you're trying to identify if there's potential moisture within there. So the scanner will measure the amplitude of the current and give you a relative reading that you can record, and you can say, okay, this reading is, say, 20, this reading is 80, so the potential for moisture in the 80 reading is a lot higher than the potential for moisture in the 20 reading. So it gives you a relative scale for the potential for moisture, and what's important about this test is following it up with inspection openings to verify those readings. So I'll give you a case study here in a little bit where we did that. It requires a good knowledge of the use of the equipment, because you have to set the scanner sensitivity and the signal strength based on the roofing system that you have. The other test here that we want to discuss is the D7877, which is electronic leak detection. And there's several different ways to do that. There's low voltage methods, which I'm not going to really get into here, but 2 types of low voltage methods, and a high voltage method, which we perform more frequently than the low voltage. But with the high voltage, you basically have a broom or a handheld wand where we're generating a current that's grounded to the roof deck. And the broom or the wand has metal bristles, and it's swept across the roof surface. And when you hit a breach in the membrane, it creates an electric arc, and it gives you a signal that, hey, there's a hole here. So you can, at that instant point of time, you can identify a hole or a failed or incomplete weld. So we really like this test because, say you have a small hole or you have an incomplete weld, and if, as Fiona was saying, if you have a roofing system that has a membrane and thick insulation and then a concrete roof deck, the time that water takes, if it's just even a small hole, to actually form a leak on the inside and for a building owner to identify that leak could be quite a bit of time. And meanwhile, we have wet insulation that no longer has an R value that we want, or we have risk for uplift failure of the roof. So really identifying those breaches early on is helpful. This test, one complication for this test is that the surface has to be absolutely dry. So when we have frost on the surface of the roof or standing water, it can be pretty complicated to do. But this test happens at the end of the roofing installation after trades are done walking on the roof. We're not going to have any more potential for holes, and then we'll do the roof or do the test. So the case study is a residence hall at a university in Iowa. It was a 200,000 square foot building, 8 stories plus a basement. We commissioned this building. Currently trying to wrap up that process, but you'll see in this case study that we're having some issues with the roof. The roof assembly consisted of a white TPO, and then a Dens deck cover board above polyiso insulation, and then a hollow core precast plank. During the design review, we recommended that they put a vapor retarder on top of the precast deck so that we could minimize the potential for air exfiltration into the roofing system, which is an issue with white roofing membranes and subsequent condensation. So we wanted to do that in the design phase. We did not get our way on that one, and the contractor decided to try to just seal up the precast as best he could at all of the penetrations, the terminations, the plank joints, and such. So no vapor retarder, but that allowed us to do the electrical the high voltage electronic leak detection, because we could create the arc with the deck below. We did 100% of the roof by both capacitance and electronic leak detection for this building. We had some issues throughout construction. One, you can see there on the left, a lot of ponding water on top of the roof. The other materials were stored on the roof. I found so many nails and screws, whatever, the knife blades on the roof, so high potential for damage. The other issue throughout construction was materials were being left out in the rain. So the polyiso was getting wet, coverboard was getting wet, and then the night seals, you can see there on the right. It's important that when we put the roofing system in, they're not going to get it in one shot. So we need to make sure that we're temporarily sealing those overnight, so we don't, if it rains or snows, that when the snow melts, or the next day, it doesn't run underneath your system and become trapped. So we had some issues with that. We identified avenues for air leakage. You can see a penetration that they installed after the fact that wasn't sealed, and then at the termination of the roof, we had an open joint down to below. So we had avenues for air leakage. They didn't do terminations of the roof real fantastic that we identified and worked with the contractor to try to get it tight. So a few issues that we identified throughout the process, which was important, rather than coming in at the end and just saying, we have issues. It's nice to try to get that done up front and make sure we do the best job we can throughout construction. But here we did the capacitance scan on the roof, and in November of 2016, we identified quite a few areas of potential moisture. We made inspection openings. Most of the openings corroborated our scans. Some of them didn't. So we came back in February of 2017, did the same testing, and the areas in green are the areas of potential moisture. So, 95% of the roof we identified having potential moisture in there. We, as I mentioned earlier, it's important to open up that roofing system and verify what you found with your capacitance scan. So we made, I think, 8 or 9 inspection openings, both at areas with potential moisture and areas that we thought would be dry, to corroborate the scans. And you can see we identified moisture in the roofing system. We also used a Delmhorst to measure the relative moisture content within materials. So we identified moisture. We were concerned with reduced thermal resistance for the insulation, loss of strength in the insulation and the coverboard and the adhesive, and then potential for water leakage long term. So in this project, it's ongoing, but we have to identify what that cause of the moisture is. But one of the things that we also did on this project was electronic leak detection, where we identified over 200 breaches in the roofing membrane. So we circle those on the roofing system, and contractor can repair them right away. So it's pretty nice, but one thing about this is not all of the breaches corresponded to wet locations. So likely we're looking at a condensation-related problem, but yet to be determined through further investigation. The last case study is really looking at air leakage testing of air barrier systems, so looking at qualitative testing through E1186, and then whole building air tightness testing with E1827. But the process is identify a quantitative number of air leakage at a certain test pressure for the whole building, and that is I'll go into that in a second, but. Why do we do this testing? Fiona touched on the fact that, hey, this is after the fact, the building's complete, the opportunity to address issues that we might find. Say we don't meet the specified requirements, what do we do about it? That can be an issue if you wait till the end of the project, so doing the testing up front becomes important. But why do we test? So we want to test for compliance with the specification, so get the quantitative value. We can validate our efforts in the commissioning process to make, hey, did we do a good job? Was this effort in commissioning, does it pay off? We can use it to motivate contractors to do a good job with the air barrier systems. We can use it to evaluate retrofit effectiveness. We've done that several times. We do a test before we have condensation problems due to air leakage. We do a test up front to determine what's the leakage rate. We retrofit the building. We do a test following and see how much did we tighten it up. And we can do this for determining air leakage rates for energy modeling. There's various air tightness requirements out there. I'm going to kind of pass through this so we can get to the case study, but 0.4 is about a normal number that you would see based on the IECC, one of the compliance paths there. And the case study is, again, we're going to use this laboratory building in Madison, Wisconsin. As Fiona mentioned, it's a large building. And we were able to do a whole building air tightness testing on a 330,000 square foot building as part of an ASHRAE study. So it was a huge undertaking to do a test like this. One thing that helped us out on that testing is that this building had some significant full height atria. So 2 very, very large atriums that allowed us to provide a single zone for the entire test. So one of the efforts up front was identifying the pressure boundary. So we need to calculate the surface area of the enclosure, and as Fiona talked about, those usually aren't just 6 sides. We have ins and outs and ups and downs and all over the place. So calculating the surface area of an enclosure can be a significant undertaking here. And then we also have to identify which doors need to be open, which doors should be closed, which dampers need to be taped off. And in this diagram, you can see the large atria areas in green. So those the upper one and the lower one are the large atria that we had to work with. So building setup was, took us hours to get this building ready to go, running around and opening up doors and, making sure the entrances were secured and students weren't going in and out was a really big deal. Installing the fans, you guys are familiar with this, but there's 3 fans per door. I think we installed 12 fans for this building. We only had to use 9. And then we had our DG 700 micromanometers that were measuring the airflow and the differential pressure simultaneously at the fans. We had our pressure taps at the roof and at the grade on all 4 facades, and we tried to shield those from the wind. We had the weather conditions that we needed. Our wind speed was below 4.5 miles per hour, and we had the right exterior temperature and interior temperature difference. And then all those fans routed back to this DDC control system that simultaneously calculates the air leakage rate with the pressure differential between inside and outside. So it calculates the air tightness and then characterizes the leaks. We also got to use the air handling system for this test as part of the research project. And here's our results. So when we looked at just the above grade enclosure, we ended up at 0.196 CFM per square foot at 75 pascals. If we looked at also the below grade, we were at 0.13 CFM per square foot. So we did identify some leaks in the building around plenum spaces. At one, there was a tunnel that connected to a vivarium. We had some leakage there. We had an air intake where we identified some leakage. But overall, we validated our commissioning efforts, and we had a pretty airtight building. So one of the important things about this is, rather than just getting the numbers, let's identify where we get the leaks. So we use ASTM E1186 to get qualitative air leakage. The big picture with E1186 is that you're not getting quantitative numbers, you're not identifying a leakage rate, but you're identifying locations where air leakage is a problem. So using smoke pencils with building pressurization. Another way that we do this throughout construction is the bubble gun test. I don't know if any of you have seen that, but with an air barrier, you put a soapy solution on the air barrier surface at seams or at penetrations, so cladding penetrations, and then you have this clear dome that has a vacuum pressure, and if a bubble forms through the soapy solution, it's a site for air leakage. And the thing to remember about that, like I said, it's a qualitative result. You're not looking for what's an air leakage rate. So that is important to remember. You can also use smoke with chambers on the outside or the inside of the building. I like this test a lot for doing throughout construction because you don't have to pressurize the entire building. And it enables detection of really small leaks. And doing E783 on a curtain wall can be pretty challenging to do, so this is another option for testing a curtain wall system for air tightness.